Hello, everyone. My name is Callen Votzke. I am a PhD student here at Oregon State University, and I am presenting here today at FLEPS 2021, my paper, Stenciled Liquid Metal Paste for Robust Stretchable Electrical Interconnects. So your first question might be, okay, what's a stretchable interconnect, and why do we need a stretchable interconnect? So really what we're looking at here is making stretchable circuits. Your standard circuit board is made of fiberglass and copper, whereas our circuits are made out of silicone and liquid metal. The idea being that you can stretch, you can strain, you can deform these circuits in any way, shape, or form, and they will survive. But so why do we need to make circuits stretchable? And the idea is that if we want to make truly wearable devices or electronic skins or even soft robots, we're going to need to be able to make electronics that are free from the rigid little boxes that electronics love to live in and have them sort of distributed throughout the body and in such a way that they don't interfere at all with the actions and motions of the wearer. If we take a look here, for example, at the soft robotics side, the idea being that we have this quote unquote soft robot, but a lot of these pieces are very hard and they're just rigid valves, rigid compressor, and really only the actuators are soft. And our goal is to be able to make a soft robot that really is just as soft as can be. The sort of gold standard is from nature, and is the octopus, because an octopus can fit through any orifice large enough to fit its beak, which is the only rigid part of the robot. And if you think about making a sort of large scale body network, most of the area will be in the interconnect itself and not sort of the circuit area, the active circuit area. So we need these stretchable interconnects. In order to make stretchable circuits, we need stretchable interconnects. One of the ways to do this is by using your standard solid metals and patterning these deformable geometries, such as the gold serpentine ribbon wire shown here, which essentially just stretch out as the circuit is strained. Another way of doing so is by using sort of silver nanoparticles or similarly conductive particles in conductive inks. Those inks are then cured and usually sintered together, and you get a percolation network rather than sort of direct conduction, but that provides a stretchable interconnect nonetheless. Our work focuses on gallium as a liquid metal for stretchable interconnects. It is liquid at room temperature, has good conductivity, about 1/10 that of copper. The only downside being that as a fluid, it's rather hard to pattern. What we do is instead modify the material properties of the gallium to make it into more of a paste-like consistency. When you add in nickel particles, you can essentially create something that's more like toothpaste and is actually able to be dispensed from a syringe. Given that it's much easier to handle a paste instead of a liquid, this lends itself to patterning the circuit through stenciling. As anyone who's ever used sort of a solder stencil can attest, it's a great way to reliably lay down a paste in very small amounts, reliably and repeatedly. So what we have here is just the basic overview of what we'll be talking about today, using an example of just a one-layer LED oscillator. So on our left here, we have the stencil, which is a piece of stainless steel. The pattern of our desired traces has been cut into the stencil openings that we see. We then fill those openings with liquid metal on a base sheet of silicone, and we get to the middle where we have the interconnect successfully stenciled. Once you remove the stencil, the liquid metal traces remain on the silicone base. And then you can assemble your circuit, and if you need to, encapsulate it in another layer of silicone such that it is fully contained. There's lots of ways to make a stencil. The way here is we use just a desktop knife plotter, available as the Silhouette Cameo. and we can import designs directly from your ECAD or MCAD program. For sort of just ease of making the stencils in-house, we cut them directly out of transparency sheets, which are just very thin sheets of acetate. But you can also have stainless steel stencils or really anything that comes in a sort of sturdy enough film. But the real sort of meat here is, okay, how do we make these circuits and how can we make multiple layers of circuits? Because making a single layer circuit isn't really that useful for circuits of any real complexity. So what we see here is a CAD drawing of the multi-layer test circuit that we made for this paper. It has 6 vias and sort of 4 endpoints, one at each corner, that allow us to probe between any two and make sure there is continuity. So the first step in making these circuits is you start with a base layer of silicone. Since all of this circuit ends up fully encapsulated in silicone, you basically just start with a bed of it. We use Smooth On EcoFlex. It comes in as a 2-part silicone. You mix it, you pour it on the bed as a liquid, and then allow it to cure overnight, and it becomes the nice springy silicone we have here. You first, once you have your stencil cut out, you just apply it to the silicone and make sure you don't have any real air bubbles and make sure the stencil is actually lying sufficiently flat. You can essentially just smother it in liquid metal paste as shown here. You then remove any of the excess paste with a squeegee. The nice part is that we reclaim almost every bit of extra liquid metal that's on the stencil. You can then remove the stencil and you're left with your traces, upon which you can place any components that you need to place for that layer. Once that first layer is populated, we then add in, we have a custom-made jig that places pins in exactly the locations of our vias. We're just 3D printing these jigs. You could imagine having a jig with a ton of hole locations and you just fill in the ones you need. But the idea being that the dowel pins essentially leave a void for the next layer in the next layer of silicone that'll become a via. We can see that here. After removing the dowel pin and pouring in another layer of silicone, we're left with this void in the silicone, and that is filled in by the next layer of stenciling. So essentially, it gives us this nice interconnect between layers. And there's no real limit to the number of times you can do this. And the advantage here being that this is ultimately a buried via. It's actually much harder with this technique to do sort of a traditional through via than to do a buried via, lending itself to even more complicated circuits. Once that next layer is made, you can apply the next layer stencil, fill it in, which fills in your vias, and sort of just repeat that process until you have as many layers as you need. Once you have all your layers, you can encapsulate it in one final layer of silicone, allow it to cure, and cut it out from the base sheet. And this is just an overview of that whole process. Now that we can make stretchable interconnects, we need to figure out how we can integrate those interconnects with your standard electronic components. What we have here is an 0805 resistor, and it has been connected to 2 liquid metal traces. When these traces are stretched, the resistor obviously doesn't stretch, but the traces will pull away from the resistor. In order to solve this and potentially keep that interconnect sound, we have tried a method of strain isolation where the area right around the resistor is essentially locally isolated from any of the stretching that the entire circuit undergoes. Because this is a relatively small area, it doesn't impact the overall stretching of the circuit. Just by putting in a tiny drop of slightly harder silicone, we can essentially isolate that strain locally. What we did is we made these dog bone strain samples, and we made three different varieties of them. One variety with strain isolation, one variety where it's just the bare resistor on the liquid metal, and one control variety where the resistor itself is actually just replaced with liquid metal. Using our custom-built stretching machine, we can stretch 7 of those samples at once and log their resistance in real time with a 4-wire resistance meter. When I do talk about stretch, basically we pick a desired strain, we stretch the sample to that strain, and then relax it. That's a single cycle. So for 10,000 cycles, we will do that stretch and relax cycle 10,000 times. What we have here is a graph of the maximum resistance during each stretch and relaxation cycle for different levels of strain, starting from 50% strain and going all the way up to 200% strain. For example, just for those of you unfamiliar with strain, 100% strain essentially means that we've doubled the length of the sample. What we see here is that the control sample, as its length increases, the resistance increases as we would expect. Whereas the non-isolated sample, after 50% strain, quickly breaks away from the control sample trend and heads off towards over 100 ohms, which is essentially sample failure. It's the limit of our measurement equipment. By comparison, the isolated sample tracks the resistance of the control sample well until about 150%. So all in all, we've shown here how you can make multiple layers of stretchable interconnects, and that strain isolation may be a viable option for improving the connection with embedded components to make those connections very robust. The authors would like to thank the Semiconductor Research Corporation for their support.